Okay, perfect. So let's get started. Hello and good morning, everyone. Welcome to the Vancouver Datajam 2021 workshops. Today's workshop is our workshop, the special topics, machine learning. My name is Zaid Haddad. I'm the facilitator for this workshop. And yeah, I'll be kind of going through the unsupervised machine learning techniques through this workshop. And I did realize that there is a typo or kind of an old description. So this workshop will be on the unsupervised machine learning as well. Oh, and I see also the GitHub link being updated here. So if you would like to use the code and follow along, that will be available through the GitHub repo on the Vancouver Datajam website, or the link is also available in the Discord channel. Okay, and the Zoom chat will be closed, so please use the Discord channel, the R Advanced, for posting any questions. And I think there's also a Google Doc for whoever is not using the Discord to post their questions, and our helpers in this workshop will be able to monitor that and let us know about the questions. All right, so just mention that for the code will be available on the GitHub. So I've already posted that under my personal GitHub, and I created one for the 2021 Advanced R workshop. It has the R Markdown notebooks, as well as the source code for those ones as well, or the R code as well. And for this workshop, I'm going to be using Databricks Community Edition. Feel free to sign up and join that one. Otherwise, you can follow along using your local installation of RStudio or whichever R client you prefer to use. Okay. So kind of getting started here. So for today's agenda, as I mentioned, I'll be walking you guys through the unsupervised machine learning. I'll do a quick introduction about machine learning, and perhaps some setups and a few kind of the package or data setups, and then we'll go into the content itself. I'll walk through kind of a very high level intro into data science, machine learning, with a focus on unsupervised, and then for unsupervised learning, we're going to focus on clustering and dimensionality reduction. From clustering, we'll look at k-means clustering and hierarchical clustering. From dimensionality reduction, we'll take a look at principal component analysis. And if we have time, we'll try to go to the practice data sets as well. So for today's schedule, we'll spend the first 50 minutes or so setting up the environment, doing the introduction into machine learning data science, as well as unsupervised clustering and k-means. We'll do a 10-minute break. Then at 10 a.m., we'll resume again into clustering, k-means, and hierarchical, and go through some examples. We'll do another 10-minute break at 10:50, and then the last hour or so, we'll try to focus on principal component analysis, and if we have time, go through some of the examples. All right, so with that one, let me scroll to the top. Okay, so as I mentioned, I'm going to be doing this on Databricks Community Edition. I've already set up my cluster as well. If you haven't done so, please also try to set up your cluster within the Databricks interface. So there's the compute option. Once you click on compute, you'll be able to create a cluster. That will take usually 5 to 7 minutes to set up. Then you can attach that to the notebooks while you follow along. Right, so quick introduction about myself. So my name is Zaid Haddad. I'm a data scientist leader at Slalom. I have previous experience in the cannabis, biotech, and molecular diagnostic fields, developing and validating end-to-end machine learning models. I have my undergrad from SFU in computing science, microbiology, and biochemistry. And today we'll be going through the special topics, our workshop introduction. As a side note, Slalom is hiring. Slalom is a modern IT consulting firm. If you're looking for kind of a new opportunity please check out careers at Slalom. Here's the link for that one. Also indicated a link for that in the introduction Slack or the Docker channel as well. Please feel free to connect on LinkedIn, Twitter, as well as GitHub to follow me or ask any questions. The code is available on GitHub as well. For this workshop, we're going to be using R. We're focusing on unsupervised learning, and this is kind of geared toward advanced R users. So there's some basic knowledge of R and tidyverse packages is expected here. So we're only going to cover introduction to unsupervised learning. We're not going to go into deep kind of data pre-processing or end-to-end or any of the detailed methods, but it's just, trying to cover as much as possible into unsupervised learning. Okay. As I mentioned, I'll be using Databricks Community Edition. However, please feel free to use your favorite R Studio or R IDE as well. So once you get your environment set up, please introduce yourself on Discord or on the Google documents, and then we'll give everybody like 5 minutes so we can get started with the introduction. While we wait for everyone to set up their environment as well as introduce themselves, I'll probably share a fun fact about myself during the pandemic and whatnot. So during the pandemic, especially last year, one of the things I tried to do myself is basically cut my own hair. So that went, at least to my expectation, I thought it went well, especially cutting it from the sides, from the front. I thought I was doing a good job. But then I didn't realize that I was not cutting my my hair evenly from the back. It's kind of difficult to do it yourself, but I thought I was doing a good job until my friends and family noticed that it was uneven. So I thought that was a totally fun fact about trying to hack things yourself during the pandemic. But at least for my professional Zoom calls and Teams calls, it looked okay from the front, but the back, obviously no one was looking at that. So thankfully I was working from home.
If you guys also just want to give a quick thumbs up when your environment is set up, that might also be helpful.
The notebooks for data. So there's a question whether we have access to the notebooks on the cloud Databricks. Unfortunately not, as I'm using kind of the community edition of Databricks. However, the R Markdown is available on my GitHub repo. So I have the R Markdown for the notebooks, as well as the source code or the R code version of those notebooks. Just make it easy if you want to load it in R for future reference. And if you want to follow using Databricks Community Edition, you can always, once you set up your workspace, you can also import the notebooks using the file upload or using a URL. And from here, you can use any of these formats. So .r, .rmd is acceptable. So you can use that to upload it. That way you don't have to copy paste. Okay, so I see the majority of people have used the thumbs up to indicate that you've set up their environment. So let's get started. Anyways, this is going to be a very brief introduction to data science. Hopefully that will give the rest time to catch up. And of course, this will be recorded just as an FYI, and the link I'm sure will be posted shortly after. All right, so just in case, if you're not familiar about data science or machine learning, I'll try to do a quick introduction about that. So what is data science? Data science, again, it's data analytics, data mining, statistics, big data, machine learning, predictive analytics. It's basically just making sense of the data. It's a multidisciplinary approach that uses stats, math, computer science, and domain knowledge and expertise to kind of make sense of that data. In terms of the data science life cycle, there's a cross-industry standard process for data mining known as CRISP-DM, and that's usually used in data science for trying to answer questions about the data or the business problem in question. So the first we start with the question that we're coming up with, the business understanding of the problem. Once we have determined that one, we need to get kind of the data. So that's where we go into the data, understanding the data and trying to kind of get that data ready for us. And the next part would be the data preparation step. And then if there's modeling, there's going to be the next step after that. And of course, it's back and forth to make sure that the data is prepared for our modeling. Then once we have the modeling done, we take a look at the evaluation step. And again, that circles back to the business understanding of the business problem to make sure that we have answered the question or the business problem at hand. And of course, that's a problem that may kind of use a life cycle. So it may have iterations and going back until we get the data or the modeling to answer our question here. Once done, of course, there's deployment in production, but let's not worry about that piece right here. Another kind of approach from Microsoft about the team data science process, they call that as an agile iterative data science methodology to deliver predictive analytics solutions and intelligent application efficiently. So again, starting with the business understanding, in terms of the data acquisition and understanding, it may involve looking at the data source, trying to determine whether the data is available, or we need to get that from different sources, having the pipeline to acquire the data, the environment setups as well, whether it's premise and cloud, et cetera, and of course, the data preparation from wrangling, exploration, cleaning, and cleansing of the data. Once we have that, of course, the next step would be the modeling, depending on the approach. There could be feature engineering, feature selection, model training, model evaluation, or in the unsupervised approach, just looking at the modeling perspective as well. So as I mentioned, there's a few types of machine learning. There's supervised machine learning, where we have classification. So it's usually binary or a few classes available. For example, spam versus not spam emails, or whether it's disease or not disease, cancer, or benign, malignant or benign. We also have regression. That's where we have continuous values. For example, the value for the dollar, or the weight gain or weight loss, or the housing market when we're trying to predict, the price of homes and whatnot. When it comes to unsupervised learning, that's where we have somewhat of two types: clustering and association, or clustering and dimensionality reduction. Clustering, that's where we try to find inherent grouping in the data. Association is finding the rules describing our data. For example, people that buy product X, they also tend to buy product Y. And of course, there's reinforcement learning, and that's basically where we have reinforcement learning algorithms or agents learning by interacting with our environments. So we covered some of the examples here. But when it comes to clustering and unsupervised learning and dimensionality reduction, usually it's not one common goal, one specific problem. It depends on the data and what we're trying to do with the data. Of course, there's a lot of applications of data science, from fraud and risk detection, applications in healthcare, internet search, targeted advertising, and so on. Okay. As I mentioned, the data science Venn diagram from Drew Conway, they always try to think about data science where it involves, machine learning, involves some kind of math and stats research, as well as the subject matter expertise or the domain knowledge, with, of course, like computing science and hacking skills to form this data science. And I've also provided references here for the materials that I'm covering here today. So that's available for additional reading. I've also included additional resources if you want to learn more about Databricks or get your hands on additional data sets. For example, Kaggle is one way to get additional data sets for practicing. And of course, meetups, Our Ladies Learn Data Science, Women Who Code, Pi Ladies Vancouver. The links are provided here. If you haven't joined them, please check them out. And of course, if you're looking for additional books and resources about R, there's the Big Book of R, and there's this website regarding how to get started with machine learning called Machine Learning Mastery. All right, so we covered kind of the big introduction here. We've got our compute set up. Now let's go into the introduction of unsupervised learning and k-means clustering. So when it comes to unsupervised learning, we don't have labels provided. Basically, we're trying to use the algorithm to focus on detecting the structures in our data, in our unlabeled input data. So we're trying to here differentiate between two things. So the first thing would be clustering. So here, clustering would be to find homogeneous subgroups within our data. So the groups will be based basically on distance between the observations. And then the second kind of part of unsupervised learning would be dimensionality reduction. And here we're trying to find patterns in the features of the data. And that will help us basically with visualization of the data as well as pre-processing for supervised learning as well. Usually when we're looking at unsupervised learning, we don't usually have one single goal. It depends on the type of data, the type of problem. And there's obviously a lot more unlabeled data available compared to labeled data. So one of the examples for clustering would be k-means clustering. So k-means clustering algorithm aims at partitioning the observations into a fixed number of k clusters. And then we try to find homogeneous clusters within our data. So in R, using the stats package, there's the k-means that will help us find those clusters and those centers. So getting started with a quick example here, we're going to use the RS data sets. Surprise, surprise. That's probably one of the most used data sets. Please kind of load the tidyverse, the cluster, and the reshape2 libraries. If you don't have them set up, please install those packages and load them within the environments. Next, we're going to load the RS data sets. We're going to use data RS. Actually, let me run this one here to make sure that my packages are loaded. So they are loaded, that's why I'm not getting the warning messages. Now I'm going to load the data sets by using data iris. And that will load our data sets. Okay, yeah, the code is available on GitHub. It's available in the pinned messages in the Discord channel. And it's also available on the Vancouver Datajam website page as well. If you go to Vancouver Datajam workshops, the GitHub repo link is available here as well. Okay, so we're loading our RS data sets. So let's take a look into the RS data set. I think I've seen in the chat that we have some people who are new to R and new to machine learning as well. So we'll explore a little bit more about our data set and what is this RS data set as well. And I'm sure a lot of you have seen this before. Bear with me while we go through this as well. So the first thing we're going to do is kind of look at the top few of observations of the data set using the head command. So head brackets RS, and that will load the top basically 6 rows of the data, or 6 observations of the data. We can also change this by, for example, going like 10, and that will provide the first 10 observations of the data. So our data here has a few columns describing the data, as well as the species. So we have the sepal length, sepal width, the petal length, and the petal width to describe each observation and which species it belongs to. And if we do a glimpse on the IRIS data sets, we can see that we have 150 rows with 5 columns. As I mentioned, we have 4 columns describing the data and then the species. So in this case, the label is available for this data set. And of course, we're using this as an example data set to help us demonstrate how clustering works and how we can look at the different groups here. So I thought before we dig into k-means and start doing some clustering, let's do some visualization using ggplot. We're going to use the IRIS dataset here, and with the gene point, we're going to have the sepal length and the sepal width with the facet graph of species to help us visualize what we're looking at here. So if we were to plot this, we can see with the sepal length and the sepal width, with the 3 different groups, we have some bit of a clear separation or some kind of separation between the 2 species here, Setosa and versicolor. However, versicolor and virginica are somewhat closer to each other, but there's some kind of differences when we look at this kind of dimension of the data. If we take a look at petal length and petal width here, we see again a different view. So again, Setosa and versicolor. Hopefully, I'm not butchering the species name here, but there is some clear separation here between versicolor and virginica. There is, slightly better separation compared to the previous plots. And digging deeper into here, one more example. So let's look at sepal length and petal length here. Again, we observe something similar as well, with slightly more pronounced kind of clusters within that data, or 3 separations between those species. Another plot we can look at is the sepal width versus the petal width as well, to just give us another view into this and give us a more of an understanding of what we're looking at here. Another way we can visualize this is looking at the box plots, again, using the sepal length, whether this can separate the data. So we can see, again, there's a clear separation with the first group here, the first species, but these 2 have somewhat of an overlap with their data points. Here again, we can see the 3 distinct groups or the 3 different species with some overlap between some of the species as well. And again, that's demonstrated here as well. So we kind of saw that in the scatter plots, which we are seeing in the box plots here. All right, so back to k-means clustering. So what we're trying to do here is partition our n observations into a fixed number of k clusters to find homogeneous clusters. So when we use the k-means function from the stats package, we're looking at, so here we see x, we see the centers and n-stars. So x here is a numeric data matrix. So it's important to indicate that it's a numeric data matrix. Centers is a predefined number of clusters. So obviously, if we don't know the number of clusters, that will be hard to kind of use that and plot them or use the k-means for that one. But that's what we're trying to determine, the number of clusters. And the n-start is basically because k-means has a random component and can have or repeated n-start times to improve the return model. So we're using the n-start to specify that to help us improve the return model. Now, if we look at the help from k-means, we see k-means is coming from the SAS package in R. So it performs k-means clustering on a data matrix, as we talked about it previously. Okay, we see, as I mentioned, talked about it, X is our numeric matrix for the data centers. We talked about a number of clusters. Then we also have the maximum number of iterations allowed. I think the default is set to 10. this can be changed as well. And start, we talked about it, having the random sets chosen. Then we can also have algorithms chosen here as well. We're not going to cover the details here, but we can see the algorithms indicated here within the package itself. And we have the trace set as false as well. Okay, so let's go into the example here. So to learn more about k-means, let's use the iris data sets. We're going to limit it to the sepal and petal length variables to help us, make it a bit easier for visualization and creating our data matrix. So the first thing we're going to do is grab the length from the names of the iris, store that in I, and then our X is going to represent kind of that subset of the iris data set, just looking at basically the length variable, the sepal and petal length. Now we're going to run the k-means. So X is our kind of matrix, a numeric data matrix coming from here. And we're setting it to have 3 different clusters, because we already know that we have 3 different species, and n start is set to 10 here. Once we do that, we're going to plot X and use the color from the clusters of CL. So once we do that, oops, let's get too much. We can see the 3 different clusters, and they're labeled here with the k-means clusters. So let's take a look at the CL or the k-means object here as well. So let's see if we can take a look at that here. So we can see that the k-means cluster returned 3 clusters of sizes 41, 51, and 58. And that will give us the means for each variable for each of the clusters. So we have the mean length for the sepal and the petal for each of the different clusters. And we can see the cluster vectors for our observations, the 150 observations we have. Okay. So yeah, we just demonstrated that just a minute ago. All right. So if we don't know the clusters within our data, and most likely that is the case when it comes to a lot of the unlabeled data, how do we approach and look at this? So we're going to try to initialize this and randomly assign the class memberships. So let's start. So we're going to set the seed to 12 here to help us with the random part here. And we're going to try to do the initialization here. So once we do that, we're going to plot our X with the colors from the initialization here. So we can see we're kind of sending up this way. It's a bit more random, trying to just demonstrate what we're trying, how we initiate this, and how we look at the k-means. So we're going to iterate through this to help us calculate the center of each subgroup. And then that will be the average of the positions in that subgroup. And each observation is assigned to the group that has the nearest center. And we can obviously stop the algorithm at a certain number of iterations, or once the centers, don't tend to move too much in terms of their distance, or they stop moving. So we can demonstrate this using this example here. So we're going to create 2 plots. We're going to have the centers, and by looking at the column means of our data. And we're going to obviously transpose that one and look at the points in space. Then we're going to also take a look at looking at the minimum from each cluster and do the plot and compare the two centers. So once we do that, we have kind of the first one here that provides the random assignments, and then here the final one would give us somewhat of a the finalize or the three groups with the 3 classes that we get out of the center and then the means of the centers. So in other words, what we're trying to achieve here is have iterations to keep iterating through the clusters until the class memberships or the cluster memberships doesn't change anymore, or there's like very little movement here. So this is demonstrated in the Wikipedia GIF image, or this kind of nice demonstration that shows how the algorithm keeps moving or iterating until we can see that it doesn't move as much or doesn't change as much going through the different iterations. So looking at this, let's try to, try to do this using R and using code of how we can do the model selection. So first, as we mentioned, we're gonna start with the random initialization. We have, different clustering results, obviously, but when we run k-means, the best outcome will be generated and will give us the smallest total number within the cluster sum of squares, and that will be the cluster being selected, or the best cluster that we're looking at. So for each cluster results, so for each observation, we're going to determine the squared Euclidean distance from the observation to the center of the cluster. Then we're going to sum all the distances. That way we have the local, it's more of a local minimum. So there's no guarantee that it's going to be a global minimum in this case. So we're going to repeat this, the k-means on our data, and trying to go through the iterations to kind of demonstrate this. So here, if we look at the two different clusters, so we're here creating two different clusters using k-means. Again, the same RS data sets that we're looking at the length here, and we're using the centers to be 3, so 3 different clusters with n star 10 and 10. So if we do this and look at the different results, we just see basically the same memberships assigned, just from the two groups here. However, if we look at this using a different instart, we can see slightly different results. And if we keep going and repeating this one more time and use the k-means for the instart again, we're going to see slightly different results as well. Now, when we compare the clusters here from CL1 and CL2 and look at the plots, we're seeing different k-mean results on the same kind of random data that we have. So how can we repeat this or determine this without having this randomness or without having to worry about that? So here, what we're going to do is to determine the number of clusters, we're going to run k-means with k equals 1 all the way to k equals n. We're going to record the total sum of squares for each value of k, and then choose the k at the lowest elbow position. And we're going to demonstrate this as well. So luckily, without having to worry about all these different calculations and different things, one easy way would be looking at the elbow position from the graph we're going to show shortly. That will help us determine the best k or the correct number of clusters within our data. So let's take a look at this and initialize kind of the sum of squares as 0. Then we're going to create 1 to 15 clusters. We're going to calculate k-means for those different 14 clusters. We're going to calculate or save the sum of squares for those ones. Then we're going to plot that to help us demonstrate what we're looking at. So if we were to do this and plot that, so here we can see our plots with the 15 different iterations, and we can see 3 is basically at the bottom or at the elbow position here to help us select for the best number of clusters available here. So another way, if we look at this or think about it in k-means, it's basically a method of vector quantization that help us partition n observations into k clusters within in each observation that belongs to a cluster with the nearest mean or the cluster center or the cluster centroid. So that will be our kind of basically serving as our prototype for the cluster. To find the optimal number of clusters, we're going to use the elbow method. So if we were to repeat this, just using 1 to 5 number of clusters, just setting up this slightly differently and using this function here. When we plot this, when we plot this here, we can see again 3 would be kind of the number of clusters that we're looking at determined by the elbow method. So again, so the process for k-means of how it works, basically we're randomly assigning points to a cluster. We calculate the center of each cluster, then convert the points to the cluster of nearest centers. If there's no change, we're done. Otherwise, we keep changing until the points convert to the cluster of nearest center, and the points don't no longer change if there's minimal change available. and able to determine the best model, the best outcome for the number of clusters. We're looking at the sum of squares. We're trying to find as many times the global optimum, which is obviously sometimes hard to do, but we try to achieve that. Luckily, we're able to do this and determine the lowest total within the number of clusters using basically the skew plot and looking at the elbow. We're looking at the elbow method to determine that. Obviously, in real world data and different data sets and larger data sets, it might be here harder and not as clear to find the elbow, but we're trying to find basically the closest number of clusters or the best way to find the number of clusters available. Yeah, so if you were to look at that in a different way in terms of visualization for the iris flowers here, if we visualize it this way, we can see the 3 different clusters, but we also see that there's an overlap between cluster 2 and 3. And I think we kind of saw that through the scatter plots and the box plots as well, where there was some kind of overlap between that data. So here we can see that the 2 components here explaining 95% or just under 96% of the point variability here available. But I wanted to kind of go through one more example or one more demonstration here. So if we're looking at the k-means cluster for the iris data sets and try to tabulate the iris species with the cluster k-means available, we see that here for cluster 1 and the first type of species, Setosa, we have 50 matching. For the second one, we can see 48 and 14, so it's not a total match here. And for the third one, we can see 2 and 36. So if we were to add basically the diagonal line here, divided by the number of observations, we can see just under 90% of the k-means cluster match with the actual species cluster available here. And as I mentioned again, cluster 2 and 3, so the versicolor and the virginica have some overlap in their features, as we were able to see in the cluster visualizations. So again, it's not a perfect way, but we were able to achieve about 90% matching with our actual clusters. So I'm gonna pause here and see if you guys have any questions. Were you guys able to follow along? We have a couple of minutes before our break, but feel free to ask any questions again in the chat, on the Discord, or on the Google Doc. No questions? That's a quiet group this morning. Okay, so we have a question in the chat asking, was the goal to kind of see how well the clusters do against the ground truth or against our labels? I mean, in this case, in this data set, I mean, it's a well-known data set and we have the known species or the known labels. We were able to kind of demonstrate and show kind of the matching or how well the clusters overlap or match with our species or our label. However, in real world scenarios and real data sets, we may not have the labels available. And the k-means clustering is one of the algorithms to help us cluster the data and find the groups or the clusters within our data. And again, different data sets could have different number of observations, noise levels, and so on. And it's not always as clear to find the correct groups or find the groups that we're looking for, the clusters within our data. But that will help us basically find out the number of clusters or the different clusters within our data sets. That also depends on the type of data we have. So as we saw here at the beginning in the box plots, as well as the scatter plots, we can see there is some overlap and not so much separation between the two species here. So that also depends on your data sets, depends on how much data is available, how much features, and whether those features help separate the different clusters within your data sets. So unsupervised learning, again, it depends on the goal. A lot of times it could have a lot of different goals. Sometimes this can be used to help us understand the data better and assess the data we're looking at, we're trying to evaluate and help us figure out what's going on. Even if you have labels, sometimes it's a good idea to take a look at clustering and unsupervised learning to just understand the data better before trying to dig deeper into supervised learning or additional modeling. But yeah, if you don't have labels available, then you're trying to use k-means clustering or perhaps more than one just clustering algorithm to help you find the number of clusters within your data. Does that answer that question? Okay, perfect. Any other questions? Going once, twice. Okay, if you have additional questions, no problem. After we come back from the break, we can answer some questions before we move on to the next kind of clustering algorithm. So it's 9:52 right now. How about we take a 10-minute break and come back 2 minutes after? And I'll see you guys in a bit. So if you can do a quick bio break. All right, it's 2 minutes after 10. We're going to get started to help us catch up with our schedule. All right, so if you have any questions from the first part, please don't hesitate to ask in the chats. Otherwise, I'm going to kind of continue with the workshop. The next clustering algorithm I'm going to be talking about is the hierarchical clustering. So we'll quickly introduce that and run through the same example, the same data sets, and see how that kind of works as well. So for hierarchical clustering, basically what we're trying to do is determine the number of clusters ahead of time, especially when we don't know the labels or we don't know the number of clusters available within our data sets. Usually there are two approaches. There is a bottom-up and top-down approach. The reason I'm saying this because when we do hierarchical clustering, we're going to be looking at a tree type, and that way we can have either a bottom-up or a top-down approach. And for us, we're going to be focusing on the bottom-up process here. So in hierarchical clustering, we're going to assign each point to its own cluster, then join the closest clusters or the points into a new cluster, and keep going until we have, there's only like one cluster. Obviously, we need to calculate kind of the difference or the point or the distance between the clusters. And that's basically determined using the distance function. And that will be kind of using that for our hierarchical clustering. So again, we're going to load the RS datasets. If you haven't done that, please load it using this command to data RS. That will load the RS datasets. If it's already loaded on the previous exercise, so that's fine. So here, what we're using the distance, this kind of function from R to help us calculate that on the RS for the first 4 columns. So again, the 5th column is basically the labels or the classes that or the species available. We're not interested in that. We want to just take a look at the features available within RS. So the first thing we're looking at here is calculating that distance. So if you look at the help function from the distance, it's again from the stats package. It's the distance matrix computation method or function. This function helps us compute the distance for the matrix using the data available between obviously the rows of that matrix. And we can see here a bit more about this. So with the distance, we're looking at x here. And again, x is the numeric matrix. So the same one as we saw for the k-means. And then the next one, we have the method. And the method will help us determine the distance we're using. So in this case, we're using the Euclidean or the default distance method by indicating this in this function. We can see here in the method documentation, we have quite a few to choose from. There's Euclidean, maximum, Manhattan, and so on to help us choose that. Then we have diagonal, upper, and P. So diagonal, that would be the logical value indicating whether the diagonal distance should be printed. Then upper, whether we're looking, it's again logical one, indicating whether we need the upper triangle of the distance matrix. And P, just the power of the Minkowski distance. And that's set to 2 as well, and as the default. So for us, we're not going to be changing anything. We're going to use the default. So that's why once we run this function, we're going to save it or return it to an object D. From D, we're going to use the H plus function to help us create that. So the H plus function, again, is from the stats package. It's the hierarchical clustering function or method here that help us run the analysis, the clustering analysis on the similarities or dissimilarities from the distance method available. Again, here we can see H plus takes D as the input. Then we have a method, and then we have numbers as well. So D is basically the dissimilarity or the similarity structure that we produce from the dist or the distance function above. And then the methods, we have few methods to choose from. So that helps us basically determine the linkage for the hierarchical clustering. We obviously have few to choose from, single, complete, average, and so on. So please don't worry about this right now. If you have time towards the end, we'll try to cover some of these as well. All right, so using those two functions, we're able to create our hierarchical clustering. If we were to print hierarchical clustering here, that will explain to us what was passed as D. So here's this one here. And we're seeing that we have the cluster method complete and distance Euclidean, and we have 150 observations passed into here. So once we have that, we can plot the hierarchical clustering to give us an idea of what kind of cluster dendrogram is available and what we're looking at here. So once we do that, we can see the different clusters available, and obviously kind of the labels here are being overlapped because our iris data set just has number, it doesn't have rows. We're just using the row numbers, which is the numbers here, to represent the different observations. If your data set had something meaningful, that will be available here, but just because we have 150, they're overlapping. Anyway, so in order to kind of dig deeper and figure out our clusters, let's go ahead and proceed into kind of cutting this or defining the clusters in our dendrogram. So we've produced the hierarchical clustering results, and we need to kind of cut the tree or our dendrogram at a specific height to help us define those clusters. So in our data set here, we're going to cut the distance at 1.5. So to help us basically get the different clusters that we're looking at. That will produce basically 2 clusters. So we can use this using 2 different ways. The first one using the cut tree function that will help us basically cut it at a certain height, or we can cut it using a certain number of clusters. So cut tree and use k equals c2 to help us determine that one. So here we're going to cut the iris hierarchical clustering results at a certain height to obtain the 3 clusters we're looking at using the height that can also be done using k as well. So here we have plotted the hierarchical clustering results we obtained. Just for visual purposes, I'm going to use the AB line at 3.9, height 3.9 to help us determine, look at the different clusters here. So in order to do this, as I mentioned, we can use cut tree. So once we do this using k equals to 3, we can see it returns 3 different clusters, so the labels for those ones for each of the observations. Alternatively, we can use this using the cut tree with the heights 3.9 to come back with the 3 different clusters. So again, as we can see this with the red line here to help us cut the clusters, that way we can see that we have the 3 clusters returned back to us. Okay, and then if you compare the results between the cut tree with 3 clusters versus the height at 3.9, we can see we have basically identical number of clusters. All right, so that one is obviously a lot more simple and straightforward when we look at it. We have a simple data set and we haven't used a lot of fancy things. But let's compare that with the k-means, the result that we got from the k-means clustering in the previous example, and see which one is correct. So here I'm going to run the k-means on the iris data set for the first 4 columns, or the first 4 variables that we have. We're going to have centers 3 with unstart 10. And we're going to also do the same using the hierarchical clustering with the distance method on the same matrix or the same data set that we have. Once we do that, we're going to run the table, so the k cluster and the cut tree as well, to help us determine that. So we can see some of the clusters are the same, but not everything is the same. Return back to us here. So another way to visualize this, we can take a look at basically the iris, petal length, and sepal length. Use the coloring from the KM clusters. So that will be our k-means results. And then we can use another one for the hierarchical clustering and just compare the 3 the clusters between the 2 algorithms. So we can see here we have this kind of the first cluster is somewhat clear. So we have the same one returned back to us, and it has a separation in the data set. That's why it's a bit distinguished or clear between the 2 algorithms. However, for the second and third cluster, we have slightly different results between the k-means and the hierarchical clustering to help us identify those clusters. And again, as we saw earlier, those 2 clusters have some kind of overlap within their features. That's why it was a bit hard to have that separation and get the clusters available for us. All right. Okay. So if we were to compare that, as we did it with the k-means for the hierarchical clustering with the species of the iris, or the labels that we have in the iris data set. So let's see how this one compares. So we can see the first species, the setosa, it lines up perfectly with the first cluster. However, the second cluster, we have a bit of a bit more misclassification or not clear separation here. And for the third one, we also have 27 that belong to that one, with 1 in the other species as well. So it's not perfect, but it helps us basically define 3 clusters and help us determine that. So any questions here before we continue? Okay, so if you have any questions, please post them in the chat, and once I see them, I can answer them. So another thing here, we noticed that our data sets, we didn't do any pre-processing. We went straight into clustering and using the distance. However, if we had a different type of data that required some pre-processing, that would be, especially if kind of the values or the scales are different, that will make it a bit difficult to do the clustering. So some of these machine learning models are going to be very sensitive to the different scales. This also applies to our unsupervised and clustering approach here. Also applies for the supervised methods as well. So when we really want to do pre-processing, it depends basically what we're trying to achieve. But when we can take a look at that, would be scaling the data. And also we're going to be looking at principal component analysis as well. But basically scaling the data will help us look at mean of 0 and standard deviation of 1. That may make that data set easier to visualize and easier for the algorithm to detect the clusters. So here we're going to use the scale function in R to help us with that, and we're going to look at the empty cars data sets for that one. So if you look at the empty cars data set, so please load the data sets within your environment, and we're going to look at the column means. When we look at the column means, we can see it's a lot more different between the different groups or the different data in this data set. If we were to look at the hierarchical clustering with the distance used here for the empty cars, same thing for the using that with the scaling function, we will notice we have two separate or totally different clustering available here. So that's why it's a bit important to make sure that your data pre-processing is applied before we jump into running any type of clustering or machine learning model. I'm not going to cover that too much into here, but I just wanted to make sure that you guys are aware of that one before trying to dig into the clustering algorithms. Okay, another thing I wanted to mention as well, when we looked at the clustering and the hierarchical clustering, there was a few methods available when we looked at that. So looking at that here, we have 4 methods, actually a bit more than that, to do the pairwise similarity between the different observations. And I'm going to try to talk about some of these linkage methods here. So as we saw, there was a few different ones from complete, average, single. I believe there's so a maximal complete linkage. It's the same thing, basically. It computes all the different pairwise similarities between our elements in the data, in the different clusters, and takes the largest value of these the similarities between the different clusters. So we usually have compact clusters in this approach. We could also use minimum or single linkage clustering, and that will look at basically the smallest differences or dissimilarities between our criterion here, and that will usually have loose clusters. Another one, we can take a look at the mean or the average linking. So I will look at the different averages of the dissimilarities. And that depends on the compactness of the clusters, on the averages and the data. We also have the centroid linkage that specifically looks at the dissimilarity between the centroids with the mean vector of the length and each element for each variable here, and the centroid from cluster 2. And there's also the Ward's minimum variance method, and that looks at the total within cluster variance, and that will help us basically come up with a pair of clusters with the smallest between cluster distance measured here. So that one also tends to produce more compact clusters. So again, depends on your data sets, depends on your approach. You could definitely try different methods for clustering, see the results that you can come back with. But again, sometimes it depends on your type of data and what you're looking at to determine at least the best method you're looking at here. Any questions? No questions at all? Okay, so we have some time before the end of our second break. I was thinking one way we can take a look at this is do a quick challenge and take a look at a practice example or practice data sets and apply both hierarchical clustering as well as k-means clustering to see kind of how things look in this data set. So we're going to try to look away from the iris data set and the different data sets. So I found this kind of data set from, it's called My Baskets data set. It's a grocery item data set available from this link right here. So if you launch this number 5 notebook, the challenge of the R Markdown or the source code, you'll have the link and you'll be able to read your data sets within kind of within the notebook without having to download it or save it separately. You can just use the reader function, read CSV with the URL. Just make sure that you loaded the above packages. And then once you load that one, we're going to take a look at basically our data set here before we proceed with the clustering approach. So once we load that data sets, let's take a quick look into this. So we see our data set that has 2,000 observations. we have 42 columns or variables for this, and that basically helps define the data set here. Okay, so we have read the data sets. We've taken a quick look at this data set. So I'm going to stop here and pause and give people probably about 15 minutes or so to try out basically both clustering algorithms, and let's see what you guys come up with. In the meantime, if you have any questions, feel free to answer, post them in the chat or the Google Docs. Otherwise, we'll check in 15 minutes at this example. All right, so let's get us started back here and figure out what we're looking at. Okay, so in this practice example, again, this data set is somewhat designed for unsupervised learning. So it's like grocery items and the quantities purchased. Each observation represents a single basket of goods that were purchased together. It's a more of an unsupervised analysis. We don't have a response type. We have, as you mentioned, 42 features, 42 columns. It's 2,000 observations, so it's a lot larger than our iris data set. So it's not as easy to find those clusters. So here we're trying to see kind of, are there any groupings within the data? So this data set is available on the GitHub link below. It's through another basically our machine learning book or online GitHub book. That's also linked in the agenda or the introduction for additional information. So we loaded this using the URL. So pressing the URL here, reading the CSV file, we're able to access this data set. So as we mentioned, 2,000 observations, 42 features. Great. Where do we go from here? Now, in order to kind of start at some point, we thought maybe it's a good idea to take a look at clustering approach. Let's go with the k-means clustering and figure out how things are looking at the first 25 clusters or so. So we're going to do it as we have done it previously. We're going to start with the sum of squares is 0. We're going to for loop or loop through the different k-means from 1 to 25. Get that sum of squares value for each one. Then we're going to plot the results to see kind of the elbow method, the elbow approach to help us determine the number of clusters available here. So to run this, we get this this plot. We can see it's not an easy one to help us figure out the elbow approach, but perhaps at number 5 here, number 5 here, gives us maybe an indication of the elbow. Again, we don't have a right answer here. It's just a way to kind of look at that. So that's kind of one approach using the k-means clustering. So if I were to do that, setting the seed, doing the k-means, and just looking at the tables of the cluster, we see the different membership or the different number of observations in each group. So more or less similar groups. Number 1 has probably the highest number, then varies along the different 5 clusters or 5 groups within our data. If we were to visualize that one in terms of the Venn diagram or a way to look at that with the components, we can see we have some overlapping of the data and the clusters. It's somewhat in the clustering in the middle. So it's probably not very helpful here. And we can see the first 2 components are only explaining about 10% of the data variability, and we'll cover kind of the component analysis and the variability in the next section. So to get me started here with hierarchical clustering, let's see what we can get out of that one and see whether the results are different or we get some better results here. So I wanted to kind of take a look at that first. I'm looking at the distance, so I'm going to use the distance as the default method. And then I'm going to use a different linkage method in my hierarchical clustering function here. And who knows what was the default, without looking at the help function, obviously, what is the default distance available in the distance method here? Please post your answer in the chat or the Google Docs. Any takers? That's a super quiet, shy group this morning.
Maybe everybody hasn't had their morning coffee yet.
Yeah, I'm still sipping through my second one. I'm not awake yet, so I totally get you guys. So we have one answer. It's saying complete, and it's actually Euclidean distance. The complete, I think that's you're referring to the linkage method, and that is the complete right here. However, for the distance, the default one is the Euclidean distance. Okay, so if I were to go with the default distance, the Euclidean distance here, and have my, actually, let's try this with the default method first and see how things look with that. So if I were to do this, keeping everything default, and I were to do the plot here, we see we have, you know, especially if I put the AB line at height 130 here, we have probably 1, 2, 3, 4, 5 different clusters or major clusters here. So how does this look if we change? Oh, apologies, I jumped a little too much, my mistake. So trying this one more time. So if I'm doing the default distance and the default method for linkage in the hierarchical clustering, and I plot that here, so we can see it's complete cluster method, and the distance is Euclidean. We have the 2000 objects or observations in this case. So we can see that it's all over the map. It's not giving us a clear, you know, number of clusters because we have a large data set. This is becoming too noisy and hard for us to take a look at that. So now we're going to try a different approach here, and let's see what if we change the you know, the linkage method here. So we talked about the different linkage method in the previous notebook, in the hierarchical clustering towards the end. There was 4 or 5 different ones that we covered. Who would think that there is a better one to use compared to this one? Okay, so we have a great question here. You know, where you're looking at the linkage methods here, is it kind of like a random trial and error to take a look at that? Or is there some kind of methodology or some approach to help us understand that? Again, it depends on your data sets and what you're looking at. It can be used using you know, trial and error. But in this case here, we know that our data sets, it's very large. We saw that from also the previous example, the k-means, especially, you know, if you're doing exploitative data analysis and you're looking at the features and your different groups. If you see there's a lot of overlap, a lot of data being centered or overlapped over each other, you want to try to you know, minimize or maximize the linkage. Same thing for the distance. Let's see any takers from in the chat or the Google Docs. Okay, so we want to try to maximize this in this case, because we have seen, especially when we go with the defaults, I think it's probably a good idea to start with the defaults. Then from there, or, you know, once you look at the exploitative data analysis, you try to figure out, okay, what do we need to do here to improve this? So now I'm going to try to maximize the distance and the linkage in my grouping here. So the next approach here, I'm gonna take a look at. Oops. Okay, so let's do that together here. So I'm going to try to go with the either the maximum or the ward distance. Oh, sorry, the ward linkage method, and see how things look from that sense. So if I were to do that, so again, the distance says the default Euclidean, and we're using the ward one. So I think if we go back to this notebook here towards the end, apologies, okay, scroll one more time. Yeah, we looked at the different methods, linkage methods here, and we saw that there's maximum. So maximum could be 1, to help us maximize or have more compact clusters. So minimum and mean, obviously we want to stay away from those guys. Centroid may not work in this case. Another one would be the ward one, and that one helps minimize the total within cluster variance, and that way we have a more compact set of clusters. Okay, so with that one, we have completed that one. So let's take a look of how we're going to see those clusters. I think I probably kind of skipped through that a couple of times and repeat the answer. But basically, we have slightly more compact clusters in this approach. So we have a bit more clarity within those clusters. So if we were to draw a line, let's say around 130, 140 here, just under the 140 mark, it will help us see the number of clusters. So let's see this guy right here. So again, that's using the HCl object we created earlier, using the wide distance and adding the line at 130 here. That helps us see that we have 5 different clusters. More or less, we have this first cluster here, the second cluster, third one. Then we can take a look at this guy here for number 4 and number 5. Of course, some of these guys are further subdivided, but at the end of the day, we're trying to look at reasonable number of clusters as well.
For example, sorry, this plot or is same theory of coalescence? Or this?
Sorry, what's that again?
Yes, the other day or another occasion, I see a theorem. This theorem said about how you can't join different group, and this theory is that coalescence theory and probability. I don't know if it's the same.
Sorry, I'm trying to understand the question again. So you're trying to see whether kind of the diagrams here is the same as the one we created above?
Repeat, please.
Could you please type your text? I think the Zoom might not be as clear. So if you could type it in the text, that will give us a better idea of the question.
Okay, thanks.
Yeah. Okay, so we'll pause here just for a bit to see this question and try to answer it. While we wait for that question, I'm gonna probably continue talking about this exercise here. So another way, okay, what if we try to maximize it a bit more and try to use a different method for the distance and keep the same linkage method here? So we're gonna basically apply the same thing, just add or change the method to maximum instead of Euclidean, and we're gonna keep the same linkage method as we used above. So if we were to run this guy right here and do the plot, how does this vary compared to the previous one? So we see slightly different clusters, but more or less we have our 1, 2, 3, 4, 5 different clusters. Or if you can think about it this way, we have 2 main clusters available at the top, depending on how you look at things. So that's kind of one different way to change it using the distance as well and the method. Obviously, if we use the maximum distance and the complete linkage method, that will provide with a different result as well. So if we're just trying to go through this and do that plot, you can see this totally kind of changes the way the clusters would look, and it's probably not as helpful as the previous ones. So again, that sometimes comes with experience as well as some kind of knowledge of your data to help you understand which distance method and which linkage method to use to help answer the number of clusters available here. So hopefully that was helpful. But again, for the person who asked the question, could you please let us know what the question again to help you answer the question? or perhaps you can post it during the break and we can talk about it once we come back. We're at 10:51 right now. Let's take our second break before we switch into the last topic for the day. So it's 10:51. Let's come back at 11:01 for our second bio break. All right, so I guess most of us are coming back from the break. So we had a couple of questions during the break. So the first question I was asking about the challenge itself, whether we finished that one, what was the results. So I'm going to answer that right now. We didn't actually quite wrap up the challenge before the break. So let's kind of go back into our challenge. So what I was demonstrating before the break, just using different, I guess, methods for the distance as well as the linkage, will provide different results and different types of clusters that we're getting here. So again, with these types of problems and supervised learning, we don't have like a golden rule or a correct answer here. However, from looking at both the k-means clustering, when we looked at the elbow method and the screw plot, as well as looking at the word distance, we can see that we have 5 different groups. However, if we're using a slightly different method for calculating the distance, so the maximum distance with the word linkage, that changes as well to provide us with a slightly different number of clusters. However, I think again, that's probably my opinion here. That probably having 5 different clusters or 5 different groups within the data might be the more appropriate answer, as opposed to when we're using a different distance. But yeah, we don't have kind of labels for this data set. So that's kind of some of the challenges to demonstrate how we can change some of these, the distance method or the linkage to provide different results. And based on that, sometimes you got to use some, some of our judgment as well as some of the exploratory analysis to help us kind of unlink that or uncover the clusters within the data. So hopefully that answered that question. We also have another question from Google Doc. I think the same gentleman was asking about this one right before the break. We didn't catch it earlier. So the question was whether the tree or the clusters that we see is the same as the result of the theory of coalescence. I'm not familiar with the theory of the coalescence here, but I believe it's different. So our cluster dendrogram, or the tree that we have here, we're calculating that one based on the distance and the linkage. So first, or the default one, is the Euclidean distance. Once we have the Euclidean distance, calculating the distance between the different observations, we're using the linkage methods to assign them the different clusters or link them together to produce this tree or cluster dendrogram, and that basically represents kind of the distance or the similarity between the different observations and the different groups. Yeah, and again, to kind of go back to answer the other question regarding the number of clusters within this data set or within the visualization. Again, with this one, I mean, it depends on how deep or how many number of clusters that you want to go for. Again, it could vary at different levels, but sometimes it's a good idea to have a small number of clusters, maybe a handful or so, to help you with your problem. But again, it depends on the goal. It depends on your data set as well. So it's not a right or wrong answer. It's more about the methodology and the approach here to help us with that. Any other questions? Okay, so there's one more question regarding this data set and whether kind of trying to find the number of items that were purchased together, 5 clusters would be considered enough. I mean, yeah, I think it's that should be a good idea here, looking at this data set. Depends on how thorough you need to be, but I think 5 clusters definitely makes sense for this data set. Okay, great, perfect. Again, if you guys have any questions throughout the workshop, please ask them on the Discord channel. You can always pause for questions or answer them at the end. Same thing if you don't have access to the Discord channel, please post them on the Google Docs. The link is provided in the Zoom, and we'll be more than happy to answer them either throughout the workshop or towards the end. All right, so we're kind of jumping to our last notebook here. So it's the one labeled with 04 PCA. PCA here stands for Principal Component Analysis. So we're switching away from clustering, and we're kind of going into the dimensionality reduction part of unsupervised learning. So the dimensionality reduction here, what we're trying to do and achieve behind this one is find features or structures in the features for our algorithms, and that will help us also in the visualization. That could be applied both in the exploratory data analysis stage, as well as grants for the supervised approach as well to help us for processing the data. So the basic principle here for reducing the dimensionality is transform the data into a new space that would summarize the properties of our data sets along a reduced number of dimensions. There are then ideal candidates that will help us visualize the data along with a reduced number of informative decisions. So what does that actually mean? Principal component analysis is a technique or a way to transform our original data set, our n-dimensional data, into a new space, into a new n-dimensional space. So the new dimensional space is going to be a linear combination of our original data. So basically there are composed of proportions of the original variables, and those new dimensions are going to be called principal components. So sometimes they're referred to as PC or principal components, and we could have several ones of them, PC1, PC2, and so on. We're expressing the data variability or the data variability is expressed along those components. So starting with the first principal component, the second, and so on. The principal components are orthogonal to each other, so they're not correlated. And usually the first or the maximum variability is captured within the first component. The second component, principal component, is orthogonal to the second one, and so on. And basically those ones here will help us capture the variability within our data and help us understand that better. So in R, we have a function called PRComp or PRComp to help calculate the principal components. So we're going to do that on our iris data sets. We're going to restrict that to the 4 variables that we're aware of to visualize the 3 different groups in the dimensions. So in other words, what we're trying to achieve with this, basically the dimensionality reduction, we're trying to find structures in our features and help us in visualizing our data set or our features in the data sets. Principal component analysis has 3 goals. So first, we're going to find the linear combination of the variables to create those principal components and maintain as much variance in the data as possible. And of course, those principal components are orthogonal to each other. So the intuition here with the XY correlation scatter plot, the best dimension is going to explain the variance in our data in kind of the linear regression line. That is usually our first principal components. And then the distance of the points from the line is basically the score, the component score, that will help us understand that. So applying the principal components with the iris data sets, so we gotta make sure that our data is centered and scaled. As we mentioned earlier, we saw that with different data sets in the k-means that will impact our data for supervised and unsupervised learning. Same applies here. If our data is not centered and scaled, we're going to get off results as well. And we're going to summarize those proportions of the variance to see what's being explained by each of the principal components. So let's go ahead and take a look at that. So if we're going to look at a random data frame, so we're going to create X and Y and just a random data set here, we're going to apply PRComp for this one. So the principal components on the XY data frame. And we're going to take a look at that. So basically here is X and Y of our random data points. So that's how it looks like as a scatter plot. And then here we're going to look at the original data with the principal components. And that basically, as we mentioned here, the dotted line will help us understand the distance or the variance of that data. The last one on the right basically looks at the data in the principal component space, and then U and dimension space that we talked about when we calculated the principal components to help us understand the variability and the grouping within our data. So a lot of times you will hear people saying PCA is not a clustering method, or PCA is not used for this. That is absolutely correct. Principal component analysis is a way to reduce dimensionality, and that can help us understand some of the clustering and understand the variance in the data to help us understand what we see in our unsupervised approach or in our unlabeled data. So here we're going to plot the iris data sets. We're going to focus on the first 4 features, and we're going to use the color to help us with the species to understand what we're looking at. So we're doing a bunch of scatter plots, and we can see here, looking at different variables. Again, we see one clear cluster and a second cluster for usually most of them, but in certain variables, we see, almost 3 clusters or slightly more separation between the different clusters. Excuse me. So what if we didn't know, the different clusters or how many clusters we have in our data? We could assume it's only 2 clusters within our data. So that is true in this case because we have such an overlap. But we're going to use the information from all the different variables to help us understand that and take a look at the variance within our data. Okay, so we're going to load our iris data set if it's not loaded already. We're going to use the PR comp here to help us run or do the principal component analysis. Again, we're going to focus on the first 4 variables, so just the numeric data, to visualize what we're looking at. So quickly, let's take a look at the PR comp function or the method in R. So that's, again, from the stats package, PR comp or principal components analysis. It basically performs that analysis on our given data matrix and returns the objective class PR comp. What does it take? Basically, the data or the model frame that we're looking at. And then we have an option to eliminate the NAs if you have NAs. We don't have that here, so we don't have to worry about it. Then, okay, those are important, center and scale. Those are used to help us center and scale the data only for this function here. It doesn't impact or change the data frame or the matrix, the original matrix that we have. Okay, cool. So let's proceed with that one. So if we were to apply the principal component analysis on the iris data sets and summarize that, we can see here the importance of the components. We look at the standard deviation, proportion of variance, and the cumulative proportion along the different components. So here we're only listing or it lists the first 4 components. Usually that should be good enough for when you're looking at the principal components. Sometimes the first 2 or the first 3 is more than enough. So we can see principal component 1, the standard deviation, the proportion of the variance. I think in here we want to focus on the proportion of variance. So more than 90%, 92.5 or so of our variance is captured by principal component 1, and only a small percentage captured by principal component 2, and so on. So we see the majority of the variance is captured by principal component 1. And even if we just look at the first 3 variables, that's almost 100% of the variance explained by the top 3 principal components. That's why a lot of times you will see people only looking at the first 2 or the first 3 principal components. That always tends to be, or not always, but the majority of the times, that's good enough to capture the variance and look at that. So if you wanted to kind of visualize that and see the variance captured here, we can look at it this way. We see that principal component 1 captures or explains 92% of the variance in our data set. This is a fancy plot to take a look at it. I'm more a big fan of the scree plots, once we plot the RSPCA object or the principal component object that we have, we see the different principal components and the variance being explained, the majority of variance being explained by the first principal component. Okay, so what? So where do we go from here? How do we use this data? So one way to take a look at our feature space or to map different clusters, we can take a look at the biplot function that will basically point or plot our points remapped or rotated along the first component analysis. And we can also have feature vectors in the same direction, help us in the same direction as the principal components to correlate that to the original data space. That will help us understand the variance and understand what we're looking at in the data. If you haven't used the biplot function within R, it's again from the stats package. It's a biplot of the multivariate data. Basically, X is the biplot of the fitted object that we're looking at. Y would be the second set of points. And then we have other variables available if needed. Usually, just biplot on the PCA object is good enough, and that will plot what we're looking at here. So once we do the biplot for the RSPCA objects, we can see kind of the two clusters. So again, because our data doesn't have proper row names or proper names for that data, we just have the row numbers. So we can see here first cluster, and then the cluster number 2 and 3 are kind of on top of each other. And we see those vectors that coming or correlated to the original data, the original space mapped here on our principal components to help us understand what is happening. And we can see, so the x-axis here is principal component 1, and the second, or the y-axis, the principal component 2, and helps us understand the direction and the variation within the features. So here we can see the petal length is the majority of that is captured in principal component 1. Somewhat limited, it might be hard to see, but there's another line, the petal width here, probably halfway or less than halfway through the petal length is being explained by principal component 1. However, when it comes to the sepal width, it's basically both, or the majority of PC2 and a little bit of PC1, and sepal length variation both by principal component 1 and principal component 2. Okay, so we've taken a look at this. Another way we can do is look at the variance from our standard deviation. So from the principal component analysis, we saw that we have the standard deviation. We can take a look at that variance and we can compute the proportion of variance explained in our data by the principal components. And if we do so, we can see that we have, again, 92.5 or almost 93% captured by the first principal component, and very little by the second, third, and fourth. If we look at the cumulative sum of the percentages of the variance, then we take a look where we see it by, again, 92% by the first one, 97, 98%, the first two components, and again, almost 100% by the third components. So that's another way if you want to calculate this, manually and take a look at that instead of just looking at the summary of the data sets. That sometimes come in handy if we're comparing or if we're trying to generate reports. So let's take a look at the first two principal components and number 3 and 4, and see when we do a scatter plot overlaid with the species, what do we see the different clusters, the different groups that we're looking at, or does this kind of add more noise to us? So the first one here, again, the most important plot for us would be the left-hand side, just because the first principal component captures more than 90% of the variance in the data. And the second principal component, a little bit, but that should be good enough to take a look at that. So when we do that plot, we can see, two main clusters or 3 clusters if we look at it that way. So we see the first one here is very clear, separation from the other cluster. And then here, the not very clear separation between the 2 clusters. We can see some kind of separation between the 2. Obviously, we're cheating here because we're using the labels from the data. but we can see there's some kind of separation. However, if we're only looking at principal component number 3 and 4, again, not a lot of variances captured with those principal components, but it doesn't help us explain the variation or the separation between the different clusters. Again, if we look at this in a different way, if we look at principal component 1 and 3 and 2 and 3, let's see how things look like as well. So here, 1 and 3, somewhat similar results to 1 and 2. We see 2 main clusters, and then there's some kind of overlap and separation between number 2 and 3, but not so visible. It's not going to be as easy to tell. Again, this is not a surprise for us because we did see that in the exploratory data analysis. Same thing for the k-means clustering as well as the hierarchical clustering. The second and third clusters kind of overlap just because of the nature of their features and the variables that they have within the data. And PC2 and 3, again, they're not providing any meaningful clusters here. And again, that is somewhat expected just because we know there's little variance captured by those two principal components. Okay, let's pause here and see if you guys have any questions about principal component analysis and PCA shown above. Okay, so there's a question in the chat. Why did we look at PC1 versus PC2 and PC1 versus PC3? So again, the most important thing for us here is to look at the results of the variance or the summary out of our principal components objects and the scree plot as well. So scrolling back to the top, when we computed the principal component analysis on our data sets and did the summary, we can see that principal component 1 has about 92%, 93% of the variance explained in this data set. Somewhat little in principal component 2, but more or less about 98% or just under 98% explained of the variance is being explained by principal component 1 and 2. So that's why we're trying to look at principal 1 and 2 and take a look at the clusters and the groups within our data. Looking at PC1 with the other ones probably doesn't make so much sense here. We just looked at all of them for the purpose of the exercise. But in this example, in this data set, it does not make sense, or there's no added value in looking at PC1 and PC3 together or any other components, but just for the practice of this. However, if we had a bigger data set with more variables and more principal components, obviously, and different variants as well explained by the different components, it will make sense to take a look at them as long as we have the majority of the variants kind of captured by those principal components. So yeah, we don't have to. Sometimes if we have a lot of features, up to 50 or 100 or so principal components, there's no need to look at all principal components, but we want to try to look at the majority of the variants as much as possible being captured by those components and take a look at them. We can take a look at the summary objects of the PCA, as well as the scree plots available from the default function here to help us understand which ones we want to look at to explain the grouping or take a look at the grouping in our data. And of course, we can do just basic plots or bar plots as well to help us understand what we're looking at when we're trying to achieve as well. And to kind of also answer the question why we look at PC1 versus PC2. So in the bar plot here, we can see there is some variance captured in PC2 for some of the features as well, not as much as the other ones, but here we have about 97, 98% of the variance. So that's, somewhat good enough for us to kind of look at the groupings and help us with our questions here. Any other questions? Hopefully that answered your question. Okay, Excellent question. So we have another question here asking about how do we read the bar plots. So perhaps let's go back. Was that more top? Okay. So let's forget about the red kind of lines and the red text shown here. Let's just compare the scatter plot here. Let's just pretend this is a scatter plot and looking at principal component 1 versus principal component 2. And it's basically the same as this scatter plot here that we're looking at of PC1 versus PC2. Instead of having the circles or the dots to present the observation, here it's giving us the numbers of the row names, the row numbers of our data sets. If you have something more meaningful, then that will have probably names or will have something a bit more interesting. So basically, we're just looking at scatter plot of PC1 versus PC2. We're trying to look at two variable scatter plot exactly. Thank you, Himalaya, for answering that one. And that will help us take a look at the data sets. Now, that helps us also add the features and the direction of the variance of those features explained by captured by PC1 and PC2 to help us understand what's driving the clusters, what's creating that variance or the separation between the clusters that we have. It will give us some understanding, some insights into our features and into our data. Okay. Any other questions? Okay. All right. So let's proceed with the rest of this one. So we kind of covered the basics of the principal components here. Let's go more talk about data pre-processing when it comes to scaling the data or centering and scaling the data. Again, it's important to check and verify that your data is scaled or you have decent data. Otherwise, some pre-processing needs to be applied before we apply any of these unsupervised or supervised learning. So in this case, it applies to principal component analysis. So again, going back to the empty cars data set that we used previously, again, that's a popular one here because we have seen it in the previous one. The co-means or the column means varies between the different groups. So what we have done here, we're looking at the biplots, the principal components. The first one is going to be scaling set to false, while the second plot on the right-hand side will apply the scaling, and that will demonstrate how the scaling is important to apply when we have different units of measure and different data that we're looking at. So if we were to run this guy right here, okay. So again, this is no scaling and this is with scaling. Again, it's not the best plot right here, and we have a lot of overlap, but it's clear to demonstrate that the plot on the left-hand side is not very helpful and meaningful, as most of the data is centered here, and we have some outliers here that doesn't help us understand what's happening and adds more noise to the data. However, when we scale our data sets and take a look at the right-hand side, again, just because we have long names and our plot here is small, it's not very helpful and clear to demonstrate this, but we can see it's a lot better than the no scaling plot, and that have a better understanding or better insights into the biplot and our principal components available here. So again, this exercise here to just demonstrate that scaling is important. It's important to check that on your data set before you proceed with this. So just some final comments on PCA before we wrap up the session for today and open it up to more questions. But when it comes to the real world data sets and data sets that we encounter every day, we always have missing data. We have other types of data that will help us, that will make it more difficult for us to run unsupervised learning or PCA or anything like this. So a lot of times we'll have missing data and we need to deal with that. depending on the type of missing data, we either need to make sure that they're encoded properly with NAs, or if the entire row or a majority of the row is missing, perhaps we need to remove it from the data. So with PCA, we don't deal with the missing data, unfortunately. So that's why it's important to drop those guys or deal with the missing data before we try to analyze it with PCA. So yeah, dropping the data is only viable if we have a small missing values. If we have a lot of missing data, then we need to look into other approaches before we apply PCA. We could either impute the data or look at some other options before we proceed with PCA, or perhaps in this case, PCA may not be appropriate in this case. Yeah. And of course, this pre-processing also applies into supervised learning as well, but we're not going to be covering that today. Also, when it comes to categorical variables, again, this is unsupervised learning as well as PCA. Sometimes that will add some issues when we're looking at the distance, and we're comparing the distance between the different levels, as that's, that's the distance or the way the categorical variables are in the data sets may impact the distance kind of calculations. And in this case, we may need to either drop the categorical data or use a combination of binary dummy variables to help us encode that or encode that data. So for example, if we have 3 categories, A, B, and C, and we want to create 2 dummy variables, we can create it this way, having 2 variables and encode the different variables. So for example, A will have 1, 0, B will have 0, 1, and C 0, 0. So this is just an example of how to deal with categorical variables when it comes to PCA, especially if we don't want to have impact on our distance calculations, which will obviously vary our PCA results at the end. And again, to just kind of recap the process for PCA or dimensional reduction in R, make sure that your data is in a tidy format. So I'm sure Haddad and others have explained that in the R textbook or the weekend's textbook. So there's a lot of packages and a lot of tutorials on making sure that your data is ready for that. Of course, we want to make sure that there's no missing data, so it's either removed or imputed. And then all data must be numeric values. So using one hot label or some kind of other encoding or feature, categorical feature relabeling would be necessary before we proceed with any type of unsupervised learning or any type of PCA in this case as well. And again, the last point here, make sure that your numeric data is standardized when we're looking at PCA. So it needs to be, for example, centered and scaled, so that way the features are comparable instead of looking at different data or noise in that sense. All right, so just kind of ending our workshop here and opening it up for questions. So we have probably 10-15 minutes or so until the end of this workshop. We're going to open it up to more questions. So if you have anything about PCA or anything we talked about today, please let me know. So I'll just recap and mention where this is available. Again, if you just joined this recently, if you go to the Vancouver Datajam website, click on workshops, the R workshop here, it has a link for the GitHub repo. So if you click on that one, that will take you straight into the GitHub repo. It has the R Markdown notebooks, as well as with the README, as well as the R code available within this directory here. If you're looking for the previous year's workshop, is also available under my GitHub repo as well. I'm not going to go into that link here. I think it was shared in the Discord channel earlier. It's this guy right here, but for today's workshop, just make sure you're looking at the 2021 Vancouver Datajam Advanced R Workshop folder. We have some time for questions. please type them either in the Google Docs, the link that was provided in the Zoom chat earlier, or in the Discord channel.
Thank you so much, Zaid, for hosting such a great workshop. It's always a pleasure having you host one of our workshops. Yeah, if anybody has any questions for Zaid, feel free to put them in the chat, or if Zaid's comfortable with you unmuting, yeah, ask your questions directly here while Zaid is around. Yeah, but thank you so much again.
Absolutely, it's my pleasure to teach it here. Hopefully, for next year, I'll be able to come back and teach one more.
Yeah.
And yeah, hopefully it was helpful for you guys for this workshop. Again, don't hesitate to ask questions. Also feel free to come off mute and ask a question if it's easier to just kind of talk about the question instead of typing it. And again, post the workshop. If you have questions, please feel free to connect on LinkedIn. Mention the Vancouver Datajam. I'll be more than happy to answer any questions. And this GitHub link where you can find the code available here. I'm going to probably try to clean up some of the content here and re-upload some of the notebooks, but it will stay there, so don't worry about it. It'll be available post-workshop as well. And again, for today's kind of unsupervised learning introduction, just meant to help us understand and kind of get ourselves, a bit more involved into unsupervised learning. And in no means it's comprehensive and detailed enough, but just a way to explore 3 different approaches or 3 different ways to, take a look at unsupervised learning and analyzing data without labels.
I have a quick question. So for the challenges, will those notebooks be updated?
Yes, I'm going to update that. Thank you for reminding me. I'll update that hopefully sometime today and post them on the GitHub as well. And you'll also find references to some of the material I was looking at, as well as the meetup links. Feel free to attend those ones. And of course, if you would like to practice more data science problems, Kaggle is probably a great place to start. That has a lot of open data sets. I'm sure you can find other examples as well for looking at and exploring different data sets and trying different machine learning algorithms. If there are no other questions, just checking the Google Doc. Last chance, I'll give 1 more minute. If not, then we'll wrap it up here. And again, thank you all for joining me today and listening in for this workshop. I hope you guys enjoyed it and enjoy the rest of your day.